Welcome back. In this video, we are going to look at the pressure loss in pipes. That is, given a certain length of pipe section L and a known diameter D and a flow rate Q, what is the pressure drop between point 1 and point 2, or as we call station 1 and station 2? This is very important in our analysis of piping systems. Now, the assumptions we're going to make here are that we have a steady flow, we're in the fully developed section, so we are not considering entrance effects or anything like that. We still have an incompressible flow, and the pressure is constant over a cross section. That is, if we are considering station 1, the pressure has a uniform distribution along the cross section over here. So the pressure only changes in the axial direction. So I've defined a CV, or a control volume in red, over here, and we need to consider which forces are acting on this control volume. So we have pressure forces that act on the control volume, and they act inward toward the control volume, and we know that it takes the form of P multiplied by the unit outward normal multiplied by the cross-sectional area. The other force that is acting in the axial direction is the force due to viscosity, or what we call the shear stress. So the shear stress, or rather the shear force, is equal to the dynamic viscosity multiplied by the velocity gradient normal to the wall. Okay. So this is the shear force at the wall. So if we consider only the forces acting in the direction of the flow, then we're going to have a net pressure force, which is our pressure force vector here, projected in the I direction. And so if we say that, positive to the right, which is the convention, then we are going to have P1 over control surface 1 multiplied by the area of control surface 1 minus P2 ds over control surface 2. And again, recall that we are saying that the properties are constant across the cross-section. So these ones can be taken out of the integral. And what we end up with is something of the form P1 minus P2 multiplied by pi d squared over 4, which is the cross-sectional area. So this is the net pressure force in the axial direction. Now, we can also define a viscous force in the axial direction, which we, of course, know to be of the form of the dynamic viscosity multiplied by du by dn, ds, and then projected in the I direction, where u is the velocity. And here, let me draw n on our little image here. So this n here is orthogonal to the wall. So what we need this velocity, we need this gradient at the wall. Okay, and so how do we go about this? Can we know this gradient in advance? In fact, for a laminar flow, we actually do have an accurate velocity profile. So we know that for a laminar flow, the velocity profile is only dependent on the radial direction in the fully developed regime, and it is equal to a velocity at the center of the pipe multiplied by 1 minus r over capital R, where capital R is the radius of the pipe. So Vc is the centerline velocity, and R, or capital R, is the pipe radius. So we can drop the partial derivative notation, given that we know that the velocity is only a function of r, and we can just express it as dv by dr. And carrying out this derivative, we find that it is equal to minus 2 Vc multiplied by r over r squared. And then at the wall, it is dv by dr evaluated at r is equal to capital R, and we find it to be equal to minus 2 Vc over r. Therefore, returning to our viscous shear force, we find that we have mu multiplied by minus 2 Vc over r, which is our velocity gradient at the wall, and then multiplied by the area on which it acts. Now the area on which it acts is the area of that pipe section. So that area will be equal to 2 pi r, being the circumference of the pipe multiplied by the length of pipe section that we are considering. So we find our result to be equal to mu multiplied by minus 2 Vc over r multiplied by 2 pi r multiplied by L. So what have we found so far? Our net forces in the axial direction are minus 4 pi multiplied by the dynamic viscosity, the centerline velocity, and the length of pipe. And the net pressure force in the axial direction is equal to pi d squared over 4 multiplied by delta p, where delta p is equal to p1 minus p2. And so these are important intermediate results that we will make a lot of use for. Okay. Let's consider our momentum balance in the x direction. So we know from CV analysis that the sum of the forces in the x direction will be equal to the time rate of change of the momentum in our control volume plus the momentum flux in and out of the control volume. Now recall at the onset that we have said that we are dealing with a steady flow. So what we're left with is just the momentum fluxes being in balance with the net force. So at the inlet, we have rho VR squared ds, and at the outlet we have rho v of r squared ds. Now, recall that we are considering in a fully developed flow. In fully developed flow, v of r is the same at 1 and 2. So therefore, these two cancel each other out. So what we are left with here is that the sum of the forces in the x direction is actually equal to 0. So it says that we have Fpx plus Fvx is equal to 0 in the fully developed region. So, using our results from here, what we are going to say is that 4 pi mu VCL is equal to pi d squared over 4 multiplied by delta p. And this allows us to find the pressure drop between 2 points, which we find to be equal to 16 mu Vc multiplied by L divided by the diameter squared. A very important result that we were able to come up with because of our knowledge of the velocity profile for a laminar flow. So this is, let's just be entirely clear, this is P1 minus P2 for a fully developed laminar flow. Now, using the centerline velocity is not always easy to use. Oftentimes we know the flow rate. Okay, so let's express this in terms of the flow rate Q. So recall that Q is equal to our velocity multiplied by the acceleration. So now we have a velocity profile, so we need to carry out the integration. So it is the integral of the product of the velocity profile multiplied by the differential area ds. And we know that for an incompressible and steady flow, Q1 is going to be equal to Q2. So the flow rate in is equal to the flow rate out. So the integral will take the form of the following. We have our known analytical velocity profile, which we multiply by the differential area given by r dr d theta. Carrying out this integration, we find that q is equal to 1/2 pi r squared multiplied by the centerline velocity. So we can say that the centerline velocity is equal to 2 multiplied by the volumetric flow rate divided by pi r squared. So if we call our previous result equation 1, then we are going to substitute into equation 1. So substituting this expression into equation 1 for Vc, we find that delta P is equal to 128 multiplied by the dynamic viscosity, the volumetric flow rate Q, the pipe section length L, divided by pi d to the power of 4. And this is the form for the pressure drop in a fully developed laminar flow that you will most often see. Okay, so again, this is P1 minus P2 for a fully developed laminar flow. It's often useful to express the pressure drop in non-dimensional form. So if we want to non-dimensionalize a pressure drop, we would need to divide it by something that has units of pressure. So why don't we divide it using the dynamic pressure. You may recall from Bernoulli's equation that the dynamic pressure is given by 1/2 rho v squared. And we can find this average velocity v as q over a. So, if we want to express our delta P in non-dimensional form, we will take our equation 2 over here and divide it by the average velocity. And what we find is that we get a result of this form. Now, for those who are observing, you might see this term over here pop up. And this is none other than the Reynolds number. So we can express our non-dimensional pressure drop as being equal to 64 over the Reynolds number multiplied by L over D. And it looks here as if I forgot a squared, so we have a D squared over here. And again, this is the non-dimensional P1 minus P2 for a fully developed laminar flow. So as we can see, for a laminar flow, the pressure drop is dependent on the diameter, so the ratio of the length over the diameter, and inversely proportional to the Reynolds number. We can generalize this by introducing what we call the friction factor. So what we just found can be expressed as delta P over 1/2 rho V bar squared equal to some friction factor F multiplied by L over D. Where for a laminar flow, the friction factor is equal to 64 over the Reynolds number. For a turbulent flow, we are not so lucky to have this neat little closed form relationship. What we can show through dimensional analysis is that for a turbulent flow, the friction factor is a function of, so why don't I call this a function g of the Reynolds number and what we call the surface roughness. So this term over here is the surface roughness. And so these values here for a turbulent flow have been determined experimentally and they are compiled in what we call a Moody diagram. So here we have a typical Moody diagram. On the x-axis, we have the diameter-based Reynolds number, which defines the flow regime in our pipe. On the secondary y-axis over here, we have the surface roughness divided by the diameter of the pipe. On the principal y-axis, we have the friction factor, which is what we're looking for. So we see over here that for our laminar flow, it follows the 64 over Reynolds number relationship. Now, for a given Reynolds number and a known friction factor, and a known surface roughness, what we can do is match up the value on the y-axis with the intersection of our surface roughness and then find the friction factor. So, for example, if we have a Reynolds number of 10 to the 6 and a surface roughness of, let's say, 0.04 over here, what we do is that we just draw a line going up to this intersection over here, and then we look left to our intersection with the principal y-axis, allowing us to find the friction factor at a given Reynolds number and surface roughness. So these curves are determined experimentally, and they are really useful when we don't have neat closed form relationships that come from the velocity profiles for a laminar pipe flow. Okay, so in this video, what we have done is that we have looked at the pressure drop between 2 points, given a certain pipe section, length L, a diameter D, and a flow rate Q. We applied control volume analysis, and we were able to carry out this control volume analysis for a laminar flow because of the fact that we have a nice analytical relationship for the velocity profile of a laminar flow. And what we found is that the non-dimensional pressure drop has the form of a friction factor multiplied by the ratio of the length over the diameter. Now, given the fact that we were able to carry out the control volume analysis for a laminar flow, we know the form of the friction factor for a laminar flow being 64 over the Reynolds number. For a turbulent flow, we still assume this same form for the non-dimensional pressure drop being equal to a friction factor multiplied by L over D, but now in this case, this friction factor having to be determined using a Moody diagram shown here.